Hello students, I welcome you all in this session of Quick Solutions for All India AIATS Test Series for JEE Mains 2020, test number 6, code A and B, subject Physics, test dated on 15th of December 2019. Let's start with question number 1. Here in question number 1, a physical pendulum made of a ring of mass m and radius r and a particle of mass m attached to it is suspended as shown in figure. It is displaced slightly in its plane and then released. The time period of its oscillation is given by. We have to find that what exactly will be the time period of this small oscillation. So for that, first I'll calculate what is the moment of inertia about this axis. This being a ring, so its moment of inertia about this axis will be mr square, and about here it is 2mr square. Plus, additionally, small mass is attached at this point, so it is m, and this distance is 2r, so it will be 4mr square. So effectively it is 6mr square. That is the moment of inertia of this rigid system about this axis. Now if it's been displaced by a small angle theta, let's say here, then the restoring torque that will be acting, it will be because of the weight of the ring and weight of this attached mass. So effectively restoring torque, that is coming out to be 3 mgr sine theta. So now we shall say restoring expression, that will be omega square theta. It will be taken as torque divided by moment of inertia, that is 3 mgr sine theta divided by 6mr square. This will cancel out, and if we approximate the sine theta to be very small as theta itself, then we are getting the value of omega to be equal to g divided by 2r square root. Got it? So here the time period will be 2 pi by omega, that will be equal to 2r by g. So we are getting the answer as option 1 here. So option 1 is the correct answer for question number 1. Now we shall proceed to next question, that is question number 2. In question number 2, assume a tunnel is made along a diameter of earth. The particle is released from rest from height r by 2 above the hole of the tunnel. With what speed the particle crosses the center of earth? This is just simply the application of the conservation of mechanical energy in gravitational field. So I would say, let this being the earth and the tunnel has been made along this line. It is at height r by 2 from here, and this is the central point here. So I would just say the gravitational potential energy of the particle at this point, it would be minus of g capital M small m. From here, this distance is 3r by 2, 3r into 2, and the kinetic energy was initially 0. Now at this point, gravitational potential energy will be minus g capital M, this will be 3 by 2r plus 1 by 2m v square. We need to find this value of v here. So I'll just place it along this direction. It will come out to be g capital M small m divided by r here. It is 3 by 2 minus 2 by 3. Fine. It will be 1 by 2m v square. This m will cancel out, and this will be 9 minus 4. 5 by 6. It will be 5 by 6. G capital M divided by r will be equal to v square divided by 2, or v will be equal to square root of 5 g capital M divided by 3r, or it can also be written down in terms of 5 gr divided by 3. Looking onto the options, we are getting option 2 as the correct answer for question number 2. Now we shall proceed to next question, that is question number 3. Here in question number 3, in a resonance column experiment, a tube of length 1 meter is completely filled with water. A longitudinal wave of frequency 416 Hz is generated above the tube, and water column is gradually decreased by an opening near the bottom of the tube. If air column in the tube vibrates in its first overtone, the height of the water column in the tube is, the speed of the sound is given to be 333 meter per second. You must be remembering the way the experiment has been carried out. Let's say it's been completely filled with water and it is vibrating with some frequency that's been given as 416 Hertz. So I would say the wavelength of this portion, wavelength would be how much? It is 333 divided by 416. This is in meter. Fine. Now it's been given that the air column in the tube vibrate in its first overtone. That means the way it will be vibrating, this will be the structure, I would say. This will be the structure. In fact, this distance will be lambda by 4, this one lambda by 4, this one lambda by 4. So effectively, the total length of the air column here would be how much? 3 lambda by 4. So calculating this value, this L1, it is coming out to be 3 by 4 into lambda, that is 333 divided by 416. If you calculate this value, you'll be getting this part to be somewhat around 60 centimeter. Fine. So it's been given that the total length of the tube was 1 meter. So the remaining portion, that is the height of the water column in the tube, will be how much? It will be 100 centimeter minus 60 centimeter. That will come out to be 40 centimeter. So that's the answer for question number 3. Option 2 is the correct answer. Now we shall proceed to next question, that is question number 4. Here in question number 4, 2 moles of an ideal diatomic gas undergoes through an isobaric expansion. It does 200 joule of work during the process. The heat supplied to the gas is. Definitely I would say total heat supplied, delta Q, should be how much? 10 Cp dt. Fine. Or delta Q, and here it is 2. Cp being how much? It is diatomic gas. So it will be 7 by 2 R dt, or I would say delta Q would be equal to 7 R dt. Fine. Another important information that is actually given here, that is 200 joule of work has been done by the gas during the expansion. So we know this is the work done. PV must be equal to how much? It is nR dt, and that's been given to be how much? It is 2R dt. This value is 200 joule. So clearly value of R dt is 100 joule. So just replacing this value of R dt in this equation, we are getting the value of Q to be equal to 700 joule. That's the answer for question number 4. It is option 4 is the correct answer. Now we shall proceed to question number 5. In question number 5, a 50 centimeter long string of mass 10 grams supports a mass of 3.2 kg as shown in figure. The fundamental frequency of the portion of the string between the wall and the pulley is. We need to find the fundamental frequency of vibration of this connected string here. So what we know, the fundamental frequency is F to be equal to how much? V divided by 2L. Got it? So it is V divided by 2L. 2L being 40 centimeter, so 4 into 10. We need to find the value of velocity or the wave velocity in this string. V will be taken as square root of tension divided by mu. Tension being 3.2 kg suspended, so it will be 32 divided by mu. It is 10 gram. This total mass of the string being 10 grams, so 10 into 10 power minus 3, and length of the string was 50 centimeter, so it will be 50 into 10 power minus 2. Solving this equation, we are getting the value of V to be equal to 40 meter per second. Now just put this value here on this part. We are getting 40 here into 10 divided by 2 into 4, so this is 10 and this is 5, that is 50 Hertz. That's the fundamental frequency here. So for question number 5, option 1 is the correct answer. Now let's proceed to question number 6.